Hello, and thank you for joining the webinar today. Today, I'll be talking about using sensible heat to improve efficiency and compressor protection in transcritical CO2 systems. My name is Michael Letnin. I'm the Senior Product Leader for CO2 Solutions at Hussmann. I'm presenting today on behalf of Systems LMP and together with our product line, the Purity CO2 system. Let's show you a little bit about this webinar and the content that will be provided. The topics today will be a little bit about the Hussmann LMP relationship, a quick abstract on the material we'll cover, the importance of superheat control, methods of superheat control, a brief design assessment, and the efficiency impact of those different superheat approaches. Lastly, we'll provide you with some conclusions and points for thought at the end of the webinar. So let's get started. Hussmann and LMP have been in partnership since 2014. We installed our very first Purity solution in 2015, the year after our partnership began. Since then, we have combined over 200 transcritical CO2 systems in operation today. That continues to grow as we speak, while we expand partnerships with both national and regional retailers. About the content today. Maintaining a proper superheat to your compressor suction group is essential in transcritical CO2 systems, especially those that will provide a long-term reliability to those retailers. A common approach to this is dumping hot gas from the compressor discharge into the suction line. While this approach works, it does come with a recurring efficiency penalty that the user pays for each year. Controlling superheat with sensible heat provides the same protection for your system and saves thousands of dollars over the system lifetime. Let's talk more about superheat control. While we said it's essential to maintain that proper superheat for your compressor groups, improper control of this will result in the return of liquid to the compressor and possibly compressor failure. Each compressor manufacturer recommends a particular level of superheat for each compressor design. This is to prevent premature compressor failures. Now, you can accomplish superheat control in two different ways. The first we spoke of, which is injecting hot gas into the suction line. The second is the one we'll focus on in this webinar, which is incorporating a heat exchanger into the suction line and using sensible heat to control the superheat. A key knowledge point here is in transcritical CO2 systems, the flash gas bypass valve is sending gas from the flash tank to the medium temp suction group. When in transcritical operation, this volume of gas can be significant. It's the addition of this flash gas, which is reducing the superheat of the medium temperature suction line. This is why there's a need to control the superheat via a secondary method. So let's talk about the first method, which is the hot gas dump. Now, this method controls superheat by using a high pressure expansion valve located on the medium temperature discharge. This valve takes hot gas from that compressor discharge and injects it back into the suction line. That injection of high temperature gas allows for an increase in the superheat in the medium temperature suction group. Now, when you look at a CO2 booster diagram today, you can see a diagram here as an example. This is a common one you would find if you did a very brief internet search. What you'll see here is that the valve and the piping for controlling that medium temperature suction group superheat, it's not there. It's a key element that's not present in most of the web searches you find, which is why we're focusing on it today. In general, you as a customer, or perhaps even a contractor, wouldn't know that that exists until you saw an actual piping diagram for your product. This leaves a gap. There's important system control information that's not present as you learn about CO2 through the internet. There should be, as I've indicated here, an additional pipe and routing on the diagram that explains how that superheat control works. Now that we've talked about hot gas dump, let's talk a little bit about sensible heat. Now, sensible heat controls the superheat by adding an inline heat exchanger. This heat exchanger is extracting heat from the discharge of the gas cooler. Now that heat is the heat exchanger is located in front of the throttling valve, so you also get the highest temperature gas. Now, A bypass valve is located on the suction group leading to the medium temperature compressors. This allows for you to control the flow of your medium temp suction through the heat exchanger. Therefore, you are now applying heat before the suction gas reaches the compressors. Let's show you a diagram of that. Here you can see the example of a diagram from the Purity CO2 systems, which indicates that as the discharge comes off of the gas cooler, it first passes through a heat exchanger. That heat exchanger then leads to the throttling valve, terminating at the flash tank. You can also see present the bypass valve, which controls the flow of the medium temperature suction through the heat exchanger. Now, when you look at this diagram, this is a clear picture of how the system is operating and functioning to maintain the superheat of that suction group for the compressors. All of the information is present and the critical system components are indicated. Let's talk quickly about the two designs. What are some advantages, disadvantages of both of them? Now, the hot gas dump does have advantages. One, it's a direct injection of heat right into that suction group. It uses very few components, which means this is also a very low-cost approach to controlling it. Unfortunately, though, there are disadvantages as well. First is by sending that gas back into the suction group, you have now sent compressed gas that you put energy into back into the system without getting any refrigeration. That is an energy loss. The gas that you're injecting into the suction manifold is of a much higher pressure as well. So as you're adding gas to control the superheat, you can see unstable suction pressures. Lastly, the temperature of the gas as it comes off of the compressor discharge is very hot. This can cause temperature shock to the medium temperature header because you are now injecting very high temperature gas into very cool suction gas. This can result in premature failure of piping assemblies in the unit. Let's talk about sensible heat. Some of the advantages here. One, because you are still using the discharge of the gas cooler and sending it to the flash tank, you don't lose any energy in controlling that superheat. As a secondary advantage, as you raise the superheat of the medium temp suction group, you also get subcooling of your gas cooler discharge, which is improving the efficiency of the refrigeration on the flash tank side. Lastly, the temperature delta between the heat exchanger and the medium temp suction group has a much lower delta than it does coming off of the compressor group. This eliminates the possibilities of very high fluctuations in temperature or thermal shock. There are some disadvantages with the sensible heat approach as well. You do have a higher initial cost. The addition of the heat exchanger is a component that would not be present in a hot gas dump scenario. Lastly, there is additional piping as you do have to consider the bypass loop that's put in place, which is controlling the flow of the medium temp suction through that heat exchanger. However, as we start to go into the efficiency analysis, you'll see that these upfront costs are really insignificant considering the long-term effects and costs associated with the hot gas dump. So let's talk about those efficiency impacts. Now on this slide, you see an example based on a real supermarket. You see many points of data here that cover the refrigeration load, the flow rates of the dump valve, the design conditions, what that compressor uses for energy for each pound of refrigerant it flows per hour, and the energy rate used in this calculation. Now, this is a unique project. This wasn't a high-rise. Now, in this scenario, a gas cooler was not an option. The roof structure was too far away from where the refrigeration would be used. The only option we had here was to tap into a water loop in the building. Now, unfortunately, that water loop was of a higher temperature, which led to transcritical operation, almost 24 hours, 365 a year. Now, if we take a look at the calculations, you can see here, if you're in this scenario and you are running transcritical 24, 365, by doing some simple calculations of taking the flow rates, how open the valve is, the compressor energy used for every pound per hour, and that 24-hour period, you can see here that you're using 1,000 kilowatt hours per day in energy in the hot gas dump scenario. Now, 1,000 kilowatt hours at 12 cents per kilowatt hours That's $120 a day. Over the course of a year, that's over $40,000. And if you consider a 20-year lifetime on a CO2 system, that's almost $900,000 in lifetime cost to control the superheat of your medium temp suction group. Now, earlier we spoke about the upside, that if you are using the sensible heat approach, you do get an additional efficiency gain. And that comes in the form of the subcooling from the gas cooler discharge. You can see here in our final bullet point that in this scenario, that we actually were able to gain an additional bit of capacity from the CO2 refrigerant because of that subcooling. For CO2, you'll gain roughly 2.5% capacity for each 1 degree of subcooling. And in this scenario, we saw that there was 2 degrees observed at this location during operation. That's roughly 5% additional capacity in addition to not the energy loss. Now, this might be an extreme example. You may not see 24 hours, 365 transcritical operation. So let's take a look at some other scenarios. Here are 2 scenarios which we've created. One of them is 6 hours a day for 60 days in transcritical operation. The second one is 12 hours a day for 60 days. Assuming that the summer period in the region you're located is roughly the same, this would really be looking at the effects of how the daily temperature fluctuates, cool nights and warm days versus warm days and very short sustained periods of cool evenings. So in the first scenario, using the same calculation methodology, you can see here in the 6 hours a day transcritical for 60 days that the cost is roughly $30 a day or $1,800 a year. Now, over the lifetime of that system, that's an additional $36,000. In scenario 2, using the same methodology, you can see that that's $60 a day or $3,600 a year. Now, that's going to add up to $72,000 over the lifetime of that equipment. Now, these are 2 very easy scenarios to consider. Now, knowing that each store, each location is slightly different, a chart has been provided that shows you a representation in terms of how many hours that your store could be operating in transcritical, ranging from 2 hours a day to 24 hours a day. Now, you also see on the x-axis the days of transcritical operation. I'm speaking to you from Atlanta, Georgia. Our summers are quite long here. Now, you may be reading this or listening to this from Maine, which has a much shorter summer period. This simple chart will allow you to look at the trajectory of these hours of transcritical operation and the rough length of your summer and create a quick approximation of what that expense would look like to you per year using the hot gas dump method. I hope this is helpful as you start to consider your options and looking at CO2. Because the sensible heat approach using the heat exchanger is something that is patented and unique to the Hussmann LMP purity systems. Let's go ahead and move to our conclusions. The first thing and the most important takeaway here is that hot gas dump, it works. However, it has an annual cost that needs to be considered as you're choosing your choice for a transcritical CO2 system. The sensible heat option eliminates that energy penalty and provides you with an additional benefit in the form of subcooling that we talked about. Now, you may be in a region that does not have long hours of transcritical operation, but as we spoke earlier, dumping high pressure, high temperature gas into the suction header can cause thermal shock to that medium temperature header. Cracks in that header could result in the loss of charge or downtime in your refrigeration. The sensible heat method is a patented design, only available on purity systems. CO2, one of its great benefits is that it does generate significant heat, and that heat can actually be used as an advantage. It's how, as we create and design our systems, that we are able to find those advantages and really put them forward. As you're considering CO2, one of the things we really hope that all retailers are doing is looking beyond just the first cost of the product. When you look beyond the first cost of the product and you look at the total cost of ownership, the numbers that we spoke of earlier really become substantial and significant. These can more than offset the initial cost for something like a sensible heat option. Lastly, as Hussmann is representing Systems LMP today and the Purity CO2 systems, reach out to your Hussmann rep. We are available. They are available. We can set up CO2-centered discussions to dive deeper into this topic and even create models that may be directly related to your supermarket or refrigeration design. In closing, I would like to say thank you for listening today. I hope you found this information useful and look forward to hearing from you if you have any questions or interest in moving forward with a Purity transcritical CO2 system. Thank you on behalf of Systems LMP and Hussmann, and have a great day.